Electric fields. Thanks for watching this video and don't forget to like, subscribe to the channel and activate the notifications. It's very important to the continuity of this channel. When an electric charge is placed near to another electric charge, it experiences a force. The electric force does not require a contact between the two charges, so we call it an action at a distance force. The region of space where an electric charge experiences a force due to other charges is called an electric field. All charged objects have an electric field around them that determines how they will interact with other charged particles. Electric fields are usually shown as diagrams with arrows. The direction of the arrows shows the way a positive charge will be pushed. Field lines point away from positive charge and towards negative charge. When a positive charge is placed in the electric field of a positive charge, a repulsive force arises, following the direction of the electric field. When a positive charge is placed in the electric field of a negative charge, an attractive force arises, following the direction of the electric field. In short, if we place a positive charge near a positively charged object, the positive charge will experience a repulsive force. Similarly, if we place a positive charge in the field of a negatively charged object, the positive charge will experience an attractive force. The imaginary line through which the positive charge moves is known as line of force. Like the electric force, the electric field is a vector. The electric field from a positive charge points away from the charge. The electric field from a negative charge points toward the charge. In other words, the direction of an electric field line is the direction a positive charge would move along. As well as understand the field pattern, we need to be able to measure the strength of the electric field. The electric field strength is defined using the concept of a positive test charge. Imagine an isolated charge Q sitting in space. We wish to know what the strength of the field is at a point P, a distance d away from the isolated charge. We put another charge, a positive charge of size small q, at P and measure the force F that acts on the charge small q due to Q. Then, the magnitude of the electric field is defined to be the ratio of the electric force exerted on a charge small q placed at that point to the magnitude of that charge. The capital letter E is the strength of the electric field at that point in newtons per coulomb. Coulomb's law can be used to find how the electric field strength varies with distance for a point charge. We replace the force F with Coulomb's law to get the new formula for electric field strength. A point charge of minus 25 microcoulombs experiences an electrostatic force of repulsion of 1.0 times 10 to the power of minus 4 newtons when it's placed in the electric field produced by a source charge as shown below. Determine the electric field the source charge produces at the point charge. We are given the magnitude of the point charge and the force experienced by it. So we use the first equation to calculate the magnitude of the electric field. Since the electric force is repulsion force, the source charge must be negative. So the electric field is directed toward the source charge. Calculate the electric field strength at a position P that is 1.5 centimeters from the center of a point charge of 1.7 microcoulombs in a vacuum. This problem concerns the electric field due to a point charge. We are given the magnitude of the charge and the distance from the charge to the field point. So we use the second equation to calculate the field magnitude. The field direction is radially outward from the positive charge. Calculate the net electric field at a point P that is 4 times 10 to the power of minus 2 meters from a small metal sphere A with a negative charge of 2.5 microcoulombs and 3 times 10 to the power of minus 2 meters from another similar sphere B with a positive charge of 1.5 microcoulombs. Since QA is a negative charge, the electric field created by QA at point P is directed toward QA from point P. Since QB is a positive charge, the electric field created by QB at point P is directed away from QB toward point P. We now calculate the electric field strength at P due to the charges QA and QB. The field at a particular place due to more than one point charge is the vector sum of the fields caused by each point charge on its own. We use trigonometry to find the angle theta.